You can go.
So, after a couple of minutes of delay, as usual in webinars, so to enable people to join, I would like to thank you everybody to be here and to attend this webinar of AutoTwin. And this is the third webinar of AutoTwin. AutoTwin is a European project focused on the definition of an overall platform able to define, enable, implement, and analyze data from digital twins in a way so to enable the creation of automatic simulation, so the automatic definition and the automatic creation of a digital part of a digital twin. Today, the webinar is focused on standards for digital twins, and for this reason, we have here Dr. Shao, who is working in NIST in the United States, and he will inform us and provide us his insights on possibilities and the utilities of standards for digital twins. So, Dr. Shao, please, the floor is yours.
Thank you, Yokoba, for the introduction. I'm honored to be here. Do you still see my screen?
Yes.
Okay, so I'll use full screen. So good afternoon, everyone. I don't see you after I put this full screen. So just interrupt me if you have questions or if I take too long. So like Yokoba introduced, I'm going to talk about standards related to digital twins in manufacturing. Things I'm from NIST. I'm going to give a very brief introduction of NIST. Then I'll talk about digital twin concept definitions and applications. I mean, for you guys, I think you know more than I do maybe already. Then our perception of industry challenges and needs, relevant standards, the consortia effort we involved, and I'll spend a little bit more time to introduce the new ISO 23247 standard, which is the first digital twin framework standard. Finally, I'm going to discuss some potential topics for research and for standardization. NIST. So we are, I don't know how many people have been here. I know, you know, and Andrea has been here and Yokoba has been here for conferences. But others, if you haven't been here, you haven't heard about it. NIST is a U.S. government agency under Department of Commerce. We promote U.S. innovation and industry competitiveness by advancing measurement science, standards, and technology in ways that enhance economic security and improve our quality of life. So we provide, perform world-leading scientific engineering research. We coordinate and manage extramural programs, supporting industry need, provide calibration services, and material standards for innovation. We have two campuses, the headquarters in Gaithersburg, Maryland. The other one is in Boulder, Colorado. We have total 7,000 people. Half of the 7,000 are federal employees. The other half includes students, contractors, visiting professors, and the guest researchers. We have had 5 Nobel Prize winners. So laboratory program, we have 5 labs and 1 center to drive innovation through measurement science and help speed up the adoption and deployment of advanced technology solutions, provide world-class unique facilities for research and development. I'm from engineering lab. I don't know if you heard about MEP. This is a public-private partnership program. NIST is the head office location. We manage 51 centers, including Puerto Rico, and the other 50 states in the United States. So this program really provide coordination, service, and support to help any manufacturers to get resources they need to succeed. We also manage and coordinate Manufacturing USA Institute. We have right now we have 16 Innovation Institute, and Jay just mentioned a new one, which is for Chips um, for America programs. So we also manage this chips money, 39 billion for incentive for manufacturers, 11 billion for. Someone have questions? No.
No, don't worry. Questions are only for after your presentation.
Okay, okay. So we have 11 billion for R&D. Right now, we're investing more than 200 million in the Manufacturing USA Institute to create a digital twin center for chips, semiconductor and packaging, assembling, manufacturing to um, develop digital twins for chips applications to make progress in this industry. Like I said, I'm from engineering lab. Advanced manufacturing is a focus area. We have 3 programs: measurement science for additive manufacturing, measurement science for manufacturing robotics, advanced manufacturing data infrastructure and analytics. I'm leading a project under MDIA, which is Digital Twins for Advanced Manufacturing, which is to develop, deploy standards and measurement science that enable manufacturers to better define, measure, analyze, and control their manufacturing systems and processes using digital twins. I don't have to convince you guys that digital how popular how important digital twins nowadays. It has been at least start talking about it or start implementing it in different industries for different kind of purposes. But what is a digital twin? Like I said, you guys probably know very well. But if you Google it, you may find more than 200 definitions in the internet. They're all different. So it's very important which definition you're taking to develop your own digital twins. Graves and Vickers first defined the concept in 2002 as a digital informational construct of physical system as an entity on its own. And the digital informational construct has to be linked with the physical system throughout the entire life cycle. So here I list a few definitions. The top 2 are for general purpose and not only for manufacturing, but the bottom 2 are for manufacturing specifically. The first one is from Digital Twin Consortium, a virtual representation of a real-world entities or processes synchronized at a specified frequency and fidelity. The second one is from ISO IEC 3173. It's about the same idea, digital representations of a target entity with data connections that enable convergence between the physical and digital states at appropriate rate of synchronization. The third one is from the ISO 23247, which I'm going to dive into a little bit more. This is for digital twins in manufacturing, a fit-for-purpose digital representation of an observable manufacturing element, also called OME, with synchronization between the OME and its digital representation. The last one is what I defined in 2018 in the paper for InterSim. I'm not going to read it here, but that shows different kind of definitions in different fields. So this is what I see the different types of digital twins for the different purposes. Starting from left to the right, with increased complexities, more decision support with great value, but you don't have to have the the simple one before you have the complicated ones. This is just showing you different kind. The first one is descriptive digital twin, which is observe what happened or happening. Those bullets are just showing some enabling technology examples. The second one is diagnostic digital twins, which analyze what's wrong, why it is happening like this. The third one is a predictive digital twin. Is to predict what's likely to happen in the future. The future could be short, could be long. And the fourth one is prescriptive digital twin. Basically, it's optimization. It's how can we make it happen as the way we want it to be. So ultimately, is an intelligent digital twin is to automatically learn and correct itself to achieve our goals. So although the digital twin concept has been known since 2002, but only until recently it's become one of the top strategic technology trends because of the advancement of relevant technologies. So how many digital twins, like complete perfect digital twins, have you guys seen? Probably not so many. That's because of developing digital twins is not that easy. Things it's a complex system of systems. That could include a highly complex data and functional subsystems, including data sensors, data collection, data processing, data management, data um, analytics, data modeling, simulations, optimization controls, data visualization. So all of these need to work together to formulate a digital twin. But it's very challenging to seamlessly integrating everything. And the reality is the ecosystem of digital twins has not been well established right now, even though some big vendors may claim they got the complete solution, but that's only like you probably need to buy everything from them. So that's because of the lack of standard. So that for the consistent way to do things, standard to support interoperability, and with issues of securities, privacies, and so a lot of the current solutions are customized solutions, just targeting the particular problem, and the approaches taken is ad hoc. So to go beyond the custom expensive digital twin to affordable marketplace of products and tools, standards really is the solution. We often talk about plug and play, which is will enable interoperability between the digital twins among digital twin component, and connectivity between the required software and hardwares from different vendors. So think about if you right now, if we go out to buy a USB drive, when you get back home, you open box and plug it into your computer, you can start working on it, right? It stores data and retrieve information. But can we do that for digital twins? Like if you purchase a digital twin from a vendor, which is the best people who knows their product, and so they are the best people to develop the digital twin of their product. Like if you get that as a bonus, or you pay a little fee, you get that digital twin. How can you plug and play in your IT infrastructure, or can talking with your other digital twins? So to accomplish this, you really need standards. You also need to develop development frameworks and tools to enable common terminologies for communication between stakeholders, and to ensure consistency. And you should have a formalized way to describe requirements for digital twin project. And of course, you need common information models, ontologies. Do you have a digital twin library which people can use to take the building blocks, and which allow them to quickly putting things together? And once you have a develop like running digital twin, how can you analyze the performance? How can you trust the decision the digital twin make? And how can you verify and validate uh, the digital twins according to the requirement or design specification? And how can you secure the digital twins and to protect the data or access of the digital twins? All of these need to be um, taken care of by a standardized way. So currently, we have involved a couple of standardization consortia effort, uh, primarily in my project. So the first one is ISO TC 184 IC4 Working Group 15. That is the working committee for the new standard ISO 23247, published October 2021. Um, Under IC4, there's an ad hoc working group on the topic of digital twin. We are collecting use cases right now. Another one's ISO IEC JTC1, IC41, which is the Internet of Things. Working Group 6 recently published two standards. One is 30173, it's for digital twin concept and the terminologies. The other one is a technical report on the use cases. I have been working with ASME for a couple of years. I'm co-chairing a working group of verification, validation, uncertainty quantification, interactions with model lifecycle. This is really mainly for the computational models, but the principles can be applied to digital twins very easily. The idea is throughout the beginning of the model, requirement to the end of life, and digital twin have almost the same uh, life cycle, starting from the concept to the retire. Um, we had the guidelines developed as a committee draft. We're going to publish it pretty soon. Then the other two really under OMG, Object Management Group. One is Industry IoT Consortium, IIC. Another one is Digital Twin Consortium. I'm co-chair of the Digital Twin Interoperability Task Group under IIC. So we're working, we just published the technical report. The other one, we have a joint working group with DTC task group. We are working on another technical report. So now I will dive into a little bit more on the ISO standard. So this is the first ISO digital twin framework standard. We just spent 3 years to publish it. And there's four parts. Part one is general principles provide some definitions, terminologies, and requirements. Part two is reference architecture. I'll show you later. Part three is the digital representation, just exemplified how to represent the physical element using information models. And information exchange is part four, which is specify the network used between physical, digital, and different layers. The standard has three key concepts. We have seen the definition, we're not going to repeat it, but the three key concepts include observable manufacturing element, OME, fit for purpose, and synchronization. The OME is really like any physical artifact, process, or behavior on the shop floor. It could be personal equipment, materials, processes, and so on. Anything you want to model or you can model. The fit for purpose is a very important concept because each digital twin should have its own objectives. It's context dependent, only need relevant data and models. Because normally when we think about digital twin, we were told what is digital twin is a complete digital replica or mirror or copy of the physical thing. So you would think, okay, you should model everything if you're talking about the digital twin or something. Like, is it possible or even necessary to model a human being, for example? How can you model a human being from inside out completely, a digital twin? It's not possible, right? But you can have multiple human digital twins depending on the different purpose of the twin. Like, you can have fashion designer just care about the look of the human, the size, or you can have like health digital twin, only monitoring certain indicators, for example, like blood pressure monitoring. But once you achieve that goal or objective of the twin, then your twin is a good one, right? You don't have to have a very complex, covers everything, but nothing works. So sometimes people complain about oh, we don't have data, we don't have enough data, and but in some cases you have too much data. You don't know what data to pick from, what data to use. So really keep it in mind. Fit for purpose, you only need those relevant data. So the purpose dictate the information content, model fidelity, and frequency of synchronization. So synchronization is the key feature in digital twin, distinguishing it from traditional modeling simulation, because this is we're talking about real time, near real time, dynamic, you know, uh, life cycle. So the synchronization between the digital and the physical um, need to be need to be synchronized based on what could be event based, could be time based. This is the reference architecture figure showed in part 2. This is a simplified version. So basically, you see the bottom one is observable manufacturing elements, which is for um, the one you want to turn, digital tuning, and you want to observe it. And the dotted line really showing the framework, the digital twin framework, including 3 layers. One is device communication, including data collection and device control. And the middle one is the digital twin modeling. The top one is user entity. So the data is collected from the physical element, and through this digital, device communication entity, feeding into the digital twin entity. So whatever derived from the digital twin will be communicated to the users, including human device systems, applications, or another digital twins. So from there, you can do a closed loop, a control. Basically, it's observe, collect, model, learn, and act. And on the side, you have some other supporting functionalities such as data assurance, data securities, and so on. So in this standard, we have 3 industry use cases to exemplify the standard, to validate the standard. I don't have time to dive into all 3, but I will explain the number 1 for a little bit detail. Number 1 is from Boeing to achieve the increased utilization with flexible schedule robotic airframe driven field system. And number 2 is from Lockheed Martin. It's using this standard-based digital twin for weight reduction of aircraft, optimizing the size and weight of the fasteners. Because before you had this digital twin, they basically use one size. So oftentimes it's too big. So they're adding, like very easily adding a couple of hundreds pounds on the airplane. So with digital twins, you can make it much lighter. Third is from the Sandvik for tool life optimization for gearbox machining. So they use the standard-based digital twins of machine part and cutting tools to come up with the optimizations. So this is for the use case number one, flexible schedule for robot drill and fill. They used to have this manual process with those huge machine, and it's everything's operated by human, static process, non-optimal, and now they have this digital twin-based automatic uh, robot cells with the dynamic and optimal process. So they normally have this big aerospace structure. Oftentimes, they even have more than 1,000 of holes and fasteners need to be done. So when the part come in, they have a different kind of conditions of assembly, meaning some holes are already drilled somewhere else, and other holes may not need to be drilled until some later time. And everything need to be tracked, to be recorded, to be digitized. And think about if a human doing all these, it's very tedious and very easily to mix up something. And now with the digital twin idea, you see the same you know architecture being mapped with this use case for layers ONE device communication, digital twin and user entity. So the OME basically are the four robots plus the big aerospace wing structure. Um, so you have the twins of the part, and then you have the twins of the drill and fill process. Then the supervisory control will kind of compare, coordinate what come in with the nominal design to find out how many holes I really need to drill in this station. So they update that and to assign which robot doing what and sequencing it and sending the schedule to the OME through the translator, and the robot control will coordinate all these operations. And the operations need the real status will be collected through empty connect standard and through OPCOA and sent up to the tunes, meaning the part will be updated in real time and reflected in the digital twin here, and the process also recording what has been done or what problem will happen. Like say one robot died, then immediately the situation will be handled, will be adjusted, and everything will be sending back, update the condition of assembly, and once everything's finished, that will be the real final state of the situation will be going downstream. So this is like like animation showing the reduced process. Here, the blue holes do not need to be drilled. So the schedule need to be adjusted accordingly. So using this standard framework, they give you a systematic views and to organize the use case and to coordinate and to promote the usage of other existing relevant standards. So like I said, digital twin just started not long ago, a few years ago, and the standard development require a few years. Until now so many digital twin specific standard has been completed and published, even though many are in the pipeline. But we can leverage, like I said, there is even one single digital twin will involve many different aspects. We can leverage existing standards for data collection, data security, information modeling, and so on. Some examples of existing standards, including some ones that have been used in the use cases. the STEP standard for design, MT Connect for the real-time operational status, QoF for um, quality representation, and OPCOA for communication, UML, SysML, automation ML, and the CMSD. CMSD is the core manufacturing simulation data. That's for like an information model representing simulation modeling. I think I'm going to skip those. This is just like in my project we have a digital twin lab. I have some equipment including CNC machine, a CMM, a robot arm. We have the options to formulate different kind of scenarios, to test a different kind of standard, identify issues, report back, and develop digital twin prototypes. Those are some work we did last summer. And I mentioned IIC before, and this is the report which is published. We're not, I mean, the IIC is an industry consortium, or we're not developing standard, but we can specify the requirements to provide to the SDOs for them to work on standards if they like. Similar for DTC. So I want to mention right now the IIC task groups is in the process of combining with DTC. So eventually, probably we don't have the IIC work task groups. Everything will be in DTC. This is just a list of some other things. I should have listed the auto twin maybe here as a European consortium. This is MXD is in Chicago. They're doing a lot of digital twin work and for the small and medium-sized enterprises. And SimData, they do a lot of PLM, digital transformation, digital thread, digital twin. I don't. You guys probably heard about this change to twin. Um, the website at least have some really nice work on projects. This IDTA is mainly working on the AAS standard. So I have some ideas for the future standardized topics, or even just for research topics. Um, I just list them in one slide. For ISO 23247, we have published 1 to 4. Right now, we're working on part 5 and part 6. Part 5 is digital thread for digital twin. Basically, want to provide principles, guidelines, and for uh, developing digital twins using the digital thread instead of ad hoc. So that's the working in progress. And part 6, I'm actually a lead for this. It's digital twin composition. No matter how good the individual standalone digital twin you developed, eventually your digital twin need to be working with other twins, other systems. So how can you make that easy? And what's the procedures? What's the principles? What's the requirement? That kind of thing. So for ISO 23247, right now it's kind of generic, only for generic for manufacturing. That's why it stayed in a little bit high level. But next, we could extending it or specialize it into a specific sectors, such as additive manufacturing, such as biomanufacturing, such as semiconductor manufacturing. So we can add specific requirement in there just to make it useful for that particular industry. And we have talked about ontologies for this framework to make it more like understandable and easy to communicate, to exchange ideas with cross domains. And the bottom ones, just a sample of topics could be developed by any standard committees or even just for research, research purpose or even PhDs, whatever. Like reusable component, how can we have those reusable component as building blocks that can be accessible, can be seamlessly integrated with existing systems or twins. Testing validation procedures for digital twins. We have been struggling with, we means everyone is struggling with what is digital twins, how to develop digital twins. But now more and more our problem will become to like, after you develop digital twins, how trustworthy this digital twin will give the user, and what kind of decision support you can help come up with, and is it validated, is it verified? Recently, there's a National Academy's report on digital twins. They kind of emphasize this VVUQ roles for digital twins. Credibility assessment of digital twins is not exactly the same as the verification validation, but in addition, adding more on the human side of the things, because it's really like how can human trust, instead of the model is correct. How can human trust the result or the recommendations? So I have mentioned this entire life cycle of digital twins because of the nature of digital twins, dynamic real time. So you need to stay valid throughout the whole life cycle, not just like only when it's in operation. And metaverse have been discussed a lot last year. So what was the relationship between digital twins and metaverse, and how can you develop metaverse using digital twins, or parallel with digital twins, or integrated with digital twins, that kind of thing. Okay, so to summarize, the digital twins is a really complex system of systems. Standard can help understand the concept, use common terminologies, follow best practice, and speed up the adoptions and implementations. Those can be the concept terminologies, vocabularies, definitions, framework guidelines, and implementations, even tools. Associate effort confirm the industry need and identify potential requirements. There are some new parts can be added to the ISO 2327 or any relevant standards. Just disclaimer, anything I mentioned for commercial is nothing really needs to recommend it. That's it. Any questions? Thank you very much.
So thanks a lot for your interesting presentation. Is there any question from the audience? We have 22 people, so please raise questions. We still have some time to be able to take advantage of this opportunity to talk with Dr. Shao.
So no questions is a good thing or bad thing?
No, I think they will come.
Hi.
There are people working on digital twins, developing technology. So I think I think they will come. So, for instance, I will start. When you think about composition of digital twins, and these digital twins probably belong to different companies, different owners. Okay.
Yeah.
How do you, so the standards helps also to, I don't know if there is a problem of data protection or protection of the algorithms of a company that are embedded in the digital twin. So when you compose, are you also taking into account these issues that are maybe not technological issues, but business issues?
Right. Yeah. No. No. Like I said, I didn't talk too much about
Mm.
the security and privacy, but that's a very important aspect, because you have to make people, you have to protect people, and you have to make them comfortable to be part of the bigger thing, right? And like to compose digital twins, I think that's why you're saying compose instead of to 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 open up with what they have, everything they have. It's really like the minimal. My understanding is the minimal required interaction between the two twins. So you just have to. Sometimes if they keep it in the black box, nothing you can do.
Yes.
I mean, even you have this protection, this security, you still need to make them to be on board. Like, okay, that's enough for us. We trust you. Now we can share. Even you have that, you promised. If they still don't trust you, they don't open up. Okay, so I see a question for human digital twins. No, actually, I don't think there's any standards for human digital twins. One reason is that, like I mentioned, it's still new, and two, it's very complex. It's not just like technology, but also psychology. Like human digital twins. It's really, we need to go back to the fit for purpose. You probably do not have you never have a complete human digital twin, but instead you can digitize some of the human judgment. Like if you have a table allow the human to enter their feeling, right, 1 to 10, and you can digitize it. You can create the model for that.
Okay. Is there any other question? Yes, Omar asked for a question.
Okay, based regarding digital twin framework from impact, who's responsible in supervising using the digital twins?
What is the question?
The question is because it's built on data that in many cases are from different departments and require different expertise. What can be done to get the most use out of it in that case? First, you ask who's responsible in supervising and utilizing the digital twins. It's really, it seems like you're asking about for a digital twin project, who's supervising, utilizing those twins, because the standard, the framework does not have, though, I mean, the standard does not know any specific cases and who's going to use it, right? Use the standard. Like it just provide a standardized way for you to think, for you to start with, for you to organize things. But once you develop this twin, it's depending on your case, right? Like if this twin is going to be utilized in a factory floor, I guess you must have someone in charge of that, uh, managing it, utilizing it, and maintaining it. The second question is about the data from different departments, different activities we done to get the most use of it. Yeah, so during the development, you really not only need computer programmers, you do need domain expert. So someone who knows the data very well, they have to work together with the modeler to specify, what's useful, what's not useful, what that means. A question concerning the new standard. Do you have a good application of work? Yeah, that new standard is the concept, the definition, they put the terminologies, they provide some. It's not only for manufacturing, but it's generic definitions as to which describe the new framework. Model-driven approach. I mean, to develop digital twins, you can use different kind of approach, right? Like auto twin. My understanding, like I said, Andrea, I talked to Julia. We actually many years ago we had this idea of automatically generating simulation models using a commercial tool, then to start from like an information model. After you're filling in all these parameters and then you make APIs and then you click, just automatically generate the layout of a simulation model. So model-driven approach is fine to build digital twin. It's just like throughout. I mean, the idea of standard approach is like during the process, try to use existing standards or reusable ways to do things, not like patching, creating something here and there. Eventually, you just made something work, but it's never going to be duplicated. Can we say that the managerial aspect of it must remain flexible and may not be standardized? They need to be requirements can vary from use case to use case. Oh, Ali. It's not. I mean, nobody said that the manager aspect it has to be standardized, right? But it's like even you have the best practice. You want to do something smart, consistent, repeatable. You don't want to invent something, then just one off. Yes, it's true. The from case to case, you have a lot of specific needs and requirements. That's why I'm saying that the fit for purpose is very important. You can have some generic approach, but when you dive into the level of detail, you may have to do something different. Any other questions?
If I can, sorry, just another clarification in the meantime, Gordon. When you talk about digital twin standards in other application fields, in addition to manufacturing, you mentioned chips, semiconductor, and so on. Are you referring, since the observable object is always an observable object, independently from the application, will the standard differ for the exchange, for the frequency of information, or because the models are different? Since the application is different, I will use different models, so with different technology, and so I need a different standard.
Actually, you know, the high level you can apply. I mean, even though you use
Yeah.
this specific term, like say, oh, observable manufacturing element. That sounds like, oh, that's only for manufacturing. But you can say you can tailor it to observable human behavior,
Yeah.
human.
Observable, physical
Yeah,
entity,
right.
right?
Observable physical element.
Yeah.
Actually, a student of mine, she was here for like a graduate program from MIT. We recently published a paper based on the 23247, but we tailored it to the aerospace applications. So that's not manufacturing element, but we just modify that to fit in that. But basically it's like something you can observe, right? And then you can collect data. Remember, I had that observe, collect, model, act, learn, act. So that's basically can be applied to anything. Depending on how detailed you want to go, right? But if you dive, like say for additive or for chips for semiconductor, they probably have something special for that particular process or particular industry. If you add those into that standard framework, that means it's not may not be reused for something totally different.
Okay.
That's why I'm saying you can extend that framework, go into next level of detail, and then to kind of describe whatever in generic for that industry, and incorporate it in that standard.
In the meantime, that the others of the group arrives with new questions, I have also one to ask. Here, we often have interest into data security, data confidentiality, and therefore the area of data spaces with the international data space standard is a pretty growing one. And I often seen relations between this concept, IDS, and the digital twin. We have also in Auto Twin this element of using IDS for digital twins. Have you ever had any experience on the topic, or do you have any thoughts on this domain?
Nothing. Even for 23247, we have not finished. Focus on too much on the data security, confidentiality, that kind of. But we know that's an area we have to deal with. That's important. We mentioned that, but we have not dived into that. I think if someone's uh, specialized in that area, that could be a good contribution because people realize it, they think it's important, but they just haven't done too much on that, or something that has done the completely apart from this area.
So we can say that probably the digital twin is still too in the early phase also to go this deep into these
Yes,
elements.
yes,
It's more an application question than a research question, probably.
yeah. I've seen a demonstration in Detroit. So they have like Siemens. They have a demonstration on this. It's like they have a production line, and they just kind of simulate a cyber attack to their system. Then immediately they cut off the line with from the rest of the internet. Then the line's still going, but that immediately detected and action taken, and next step is planned.
Okay, thank you. As I mentioned, we have this thematic in AutoTwin, and we are also facing the difficulty of the fact that probably is a very applied element into a very innovative topic.
Yep.
Yeah. It's fine.
Any other question? Else, I think more or less we used the time we planned. So if there is anything else as questions or doubts or interest or things to be specified, I think we can thank Dr. Shao for his insights on the standards of digital twins. And I would say I wish you a very good day, and thanks for being here.
Thank you for having me. Thank you very much.
Thank you, Gordon. Thank you a lot.
Thanks a lot. Have a nice day.
Yeah, you too. Bye-bye.
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 Bye. Thank you.